imagine, just for a second, you're standing way out, like at the very edge of our known solar system. Looking back, what would you see? This incredible sort of glittering collection of worlds and stars, right? All held together by one star. You got to wonder, how did our cosmic home, this amazing system, actually come to be? So today we're doing a deep dive into the solar system itself. We're talking about our sun, obviously, and, well, everything that orbits it, big or small. Everything held in this gravitational grip. It's this huge dynamic place shaped over billions of years and honestly full of some real surprising stuff. Our mission here is to quickly but thoroughly explore how it formed, get a handle on its general layout, meet some of its inhabitants, from boiling hot planets to freezing dwarf worlds, and kind of figure out our own place in the bigger picture, the Milky Way. We've pulled out the key bits from our source material to help you get up to speed without drowning you in details. Okay, let's unpack this cosmic story. From the sun's fiery core right out to the icy edges beyond Neptune.
Yeah, absolutely. It's a journey that tells us not just what's out there, but it also gives us these fascinating clues about how systems like ours form, how they evolve, and maybe what makes our own solar system, well, kind of special.
Okay, so to kick off this huge story, where do we even begin? How did this whole, complex system actually start?
Well, the story really gets going about 4.6 billion years ago. And what's really interesting is that our solar system didn't just pop up on its own. It actually came from the gravitational collapse of this dense patch within a much, much bigger cloud of gas and dust, a molecular cloud. And this process probably made several stars, not just our sun. So as this cloud, this pre-solar nebula collapsed, it started spinning faster. That's just physics, conservation of angular momentum. And that spinning flattened it out into this huge disk, a protoplanetary disk. Think of a giant swirling pancake of gas and dust, maybe 200 AU across.
Whoa, 200 AU. Remind us what an AU is again.
Right, good point. An AU is an astronomical unit. It's basically the average distance from the Earth to the sun. So 200 times that distance across. Pretty huge. And right at the center, you had this hot, dense protostar, our baby sun, essentially. And inside that swirling disk, planets started to form through something called accretion. Basically, dust and gas particles started clumping together because of gravity, making bigger and bigger bits.
Okay, and I remember reading something about a frost line being super important here.
Yeah.
How did that shape which planets formed where?
Oh, hugely important. Critically important, really. Think of it like this. Closer to the young sun, inside this frost line, which was roughly between where Mars and Jupiter are now, about 5 AU out together, it was too hot for things like water ice or methane ice to stay solid. Only stuff with really high boiling points, like metals and rock, silicates, could condense.
So that's where the rocky planets came from.
Exactly. That's why we have Mercury, Venus, Earth, and Mars, smaller, denser, rocky worlds in the inner solar system. But beyond that frost line, it was cold enough for those icy compounds, water, ammonia, methane, to freeze solid, and there was way more ice available than rock and metal.
Ah, so more building material right there.
Precisely. This let the cores of the outer planets Jupiter, Saturn, Uranus, Neptune grow much, much bigger, massive enough that their gravity could pull in and hold on to enormous amounts of hydrogen and helium gas, the lightest and most abundant elements around. That's how they became gas giants and ice giants. And then pretty quickly, in cosmic terms, maybe within 50 million years, the pressure inside that protostar got high enough to kickstart nuclear fusion. Hydrogen started fusing into helium. Bang! The sun switched on as a proper star.
And that solar wind you mentioned.
Oh, right. Once the sun ignited, its solar wind, this powerful stream of particles blowing outwards, basically blasted away most of the leftover gas and dust from that disk. But, the story didn't just stop there. The system kept evolving. There are theories like the NICE model, which suggests the giant planets actually migrated around quite a bit early on, shuffling things up, scattering smaller bodies. It was likely a pretty chaotic period.
That sounds incredibly turbulent. So things have calmed down now. Is our solar system stable today, or should we expect more drama?
Well, on our timescales, human timescales, yeah, it seems pretty stable. But if you look over billions of years, it's technically chaotic. Though, the chances of another star just wandering through and messing things up are incredibly tiny. The real long-term drama is going to come from the sun itself.
Right. The sun won't last forever. That's kind of a mind-bending thought. What's the timeline on that?
Yeah, it is. So our sun's in its main sequence phase now, just steadily burning hydrogen. It's got about 10 billion years total in this phase, and we're roughly halfway through, give or take.
Okay, so we've got some time.
We've got about 5 billion years, yeah. But after that, things get dramatic. The sun runs out of hydrogen fuel in its core. Its core will contract and heat up, causing the outer layers to swell up massively. It'll become a red giant, expanding maybe 260 times its current size.
Whoa. What does that mean for the planets?
Bad news for the inner ones. Mercury and Venus almost certainly vaporize. Earth. Well, it'll become completely uninhabitable long before that, but it might get swallowed up too, or at least scorched beyond recognition.
Yikes.
Yeah. Eventually, after the red giant phase, the sun will shed those outer layers, puff them off into space, maybe forming a beautiful planetary nebula, and what's left behind will be its core, a super dense white dwarf. About half the sun's original mass, but squeezed down to the size of Earth.
That future really underscores the sun's power. Let's talk about its dominance now. How much does it really control things?
It's almost everything. I mean, the numbers are wild. The sun itself accounts for something like 99.86% of all the known mass in the entire solar system. Everything else, planets, moons, asteroids, comets, is just leftover fraction.
That's incredible.
It is. It's a G2 type star, pretty typical, converting hydrogen to helium, pouring out energy, mostly as light we can see. And importantly, it's what astronomers call a populationist star, meaning it's got a higher amount of heavier element stuff, heavier than hydrogen and helium, which astronomers just call metals. That was crucial, having those heavier elements available to actually build rocky planets like Earth. And its influence goes way beyond just light and gravity. There's the heliosphere, this giant magnetic bubble blown by the solar wind.
It's a solar wind. That's the stream of particles.
Exactly.
Yeah.
Charged particles constantly streaming outwards from the sun at incredible speeds, like millions of kilometers per hour. This fills up the space between planets, creating the interplanetary medium. And when the sun gets active solar flares, coronal mass ejections, it sends out bigger bursts. That's space weather.
And that's what causes auroras.
Yep. When those energetic particles hit a planet's magnetic field, like Earth's, they get funneled towards the poles and smash into atmospheric gases, making them glow. That's your aurora borealis in Australis. Beautiful, but also a sign of the sun's constant activity. Okay, let's zoom back in then to the inner circle, closer to the sun, the rocky neighborhood.
Right, inside that frost line we talked about, less than 5 AU out. This is where things are primarily made of silicates, rock, and metals. You've got the 4 terrestrial planets here and also the asteroid belt. These inner planets, Mercury, Venus, Earth, Mars, they're all pretty dense, solid surfaces, mostly rock and metal. Generally, they have few moons, or none at all, and no ring systems like the giants do. Many have atmospheres, though they vary wildly, and you see common features like impact craters and signs of geological activity like volcanoes or tectonics.
So quick tour. What's unique about each?
Sure. Mercury, smallest planet, basically no atmosphere. It gets unbelievably hot on the sunny side, like 420 Celsius, and freezing cold, minus 170 C on the night side. Huge temperature swings. It's mostly a big iron core with a thin rocky crust. Venus, often called Earth's twin because it's similar in size, but oh boy, is it different. It's got this incredibly thick carbon dioxide atmosphere that traps heat like crazy, a runaway greenhouse effect. Surface temps are over 400 C, hotter than Mercury even, and the air pressure is crushing 90 times Earth's. Very volcanic, no magnetic field.
Not exactly welcoming.
Not at all. Then Earth, our home. The only place we know of with liquid water consistently on its surface, and of course life, its atmosphere with all that nitrogen and oxygen, is unique and actually shaped by life. We've got active plate tectonics constantly recycling the crust, and our moon, which is pretty large compared to Earth, relatively speaking, and finally Mars, the red planet, about half Earth's size. That red color comes from iron oxide rust, basically. It has a very thin CO2 atmosphere now with polar ice caps. It used to be warmer and wetter, we think, but it lost its global magnetic field billions of years ago, which allowed the solar wind to strip away most of its atmosphere.
And it's 2 little moons.
Phobos and Deimos, tiny lumpy things. Most scientists think they're captured asteroids rather than moons that formed with Mars.
Okay, and between Mars and Jupiter, we hit the asteroid belt. Not like Star Wars, right? You don't have to constantly dodge.
Huh. No, definitely not. That's a great Hollywood myth. The asteroid belt is this big, torus-shaped region, mostly between Mars and Jupiter. And yeah, it's not to be leftover material from when the planets were forming. Stuff that couldn't quite clump together to make a full planet, mostly because of Jupiter's massive gravity constantly stirring things up.
So how much stuff is actually in it?
Well, there are probably millions of objects bigger than a kilometer across, maybe tens of thousands we know of. But the belt is huge. It's incredibly sparse. Spacecraft fly right through it all the time without any problems. The total mass of all the asteroids combined is tiny, less than a thousandth of Earth's mass.
Still, there are some big players in there, aren't there?
Oh, absolutely. The most famous is Ceres. It's the largest object, about 940 kilometers wide, and it's actually classified as a dwarf planet, the only one in the asteroid belt. It's
Yeah.
round, and there's even evidence it might have had ice volcanoes, cryovolcanism in the past, and it has a super thin water vapor atmosphere.
Wow. And Vesta.
Vesta is the second biggest. It's interesting because it's more like a rocky protoplanet, and it's got these two enormous impact craters on it. We actually have pieces of Vesta here on Earth. Certain types of meteorites have been matched to its composition. It's like getting free samples delivered.
That's cool. Any others worth mentioning?
Well, there's Pallas, the third largest, and then you have the Trojan asteroids. These aren't strictly in the main belt. They hang out in these special stable points called Lagrange points, 60 degrees ahead of or behind a planet in its orbit. Jupiter has heaps of them, like huge swarms. Shows how gravity shapes things.
Okay, moving outwards then. Beyond the asteroids, beyond the frost line, we get to the giants.
The behemoths, yeah. This is where things get really different. Because they formed farther out, these objects incorporated a lot more volatiles, things like water ice, ammonia ice, methane ice. This is the realm of the 4 giant planets. They're huge families of moons and those spectacular ring systems. And these 4 guys, they make up something like 99% of all the mass orbiting the sun, besides the sun itself.
So they really dominate the outer system. Let's meet them. Jupiter first.
Jupiter, king of the planets. Biggest and most massive by far. You know it from those distinctive cloud bands, the Great Red Spot, that giant centuries-old storm. It has an incredibly powerful magnetic field generating intense auroras and moons. It's got nearly 100 confirmed now.
Including those big ones Galileo saw.
Exactly, the Galilean moons.
Yeah.
Io, Europa, Ganymede, and Callisto. Ganymede is bigger than Mercury. Io is incredibly volcanic. Europa might have a subsurface ocean. They're like planets in their own right. Jupiter also has faint rings, probably made of dust kicked off its inner moons.
Then Saturn, the one with the obvious bling.
Saturn, yeah, famous for those stunning, easily visible rings made of countless particles of ice and rock. It's another gas giant, mostly hydrogen and helium like Jupiter, but slightly less dense. It also has a ton of moons, over 270 confirmed now, I think.
Wow. Including Titan.
Including Titan. That's a really special one. It's the only moon in the whole solar system with a thick, substantial atmosphere. Mostly nitrogen, kind of like early Earth, but much colder. It has lakes and rivers of liquid methane and ethane on its surface. Just fascinating.
Okay, next are the ice giants, right? Uranus and Neptune. What makes them different?
Right. While Jupiter and Saturn are mostly hydrogen and helium, Uranus and Neptune have much higher proportions of heavier elements, particularly those ices, water, ammonia, methane beneath their hydrogen-helium outer layers. That methane gas is what gives them their bluish-green cyan colors.
And Uranus is the odd one out, isn't it? Orbiting on its side.
Yeah, Uranus is tilted over completely, more than 90 degrees, so it basically rolls around the sun on its side, leading to really extreme seasons that last for decades. It's got a set of rings, too, darker than Saturn's, and a good number of moons. Neptune is the farthest official planet now. Similar blue color to Uranus, sometimes shows big, dark storm spots like Jupiter's Great Red Spot, but they seem to come and go. It also has rings and moons.
Any standout moons for Neptune?
Definitely Triton. It's Neptune's largest moon, and it's really weird. It orbits Neptune backwards compared to Neptune's rotation or retrograde orbit. This suggests it was probably a captured object, maybe from the Kuiper Belt, and it's geologically active. It has geysers erupting nitrogen frost. Pretty cool for somewhere so far out and cold.
And there are other smaller bodies out there, too. Centaurs.
Yeah, the centaurs. These are sort of icy, comet-like objects whose orbits cross the paths of the giant planets generally found between Jupiter and Neptune. They're thought to be escapees from the Kuiper Belt kicked inwards by gravitational nudges. Some of them even develop fuzzy atmospheres, comas, like comets do when they get closer to the sun. And one of them, Chiriclo, actually has its own rings.
Rings around a centaur. Wow.
Yeah, that was a surprise discovery. Shows how complex even these smaller bodies can be.
So even beyond Neptune and these centaurs, the solar system just keeps going out into this third zone.
Oh yeah, it gets really vast and sparsely populated out there. This is the realm beyond Neptune, the trans-Neptunian region. It's overwhelmingly made up of thousands upon thousands of small, icy worlds, mostly rock and ice. It's like a deep freeze archive of the early solar system. The first region we hit is the Kuiper Belt, Think of it like a much bigger, much icier version of the asteroid belt. It's this great donut-shaped ring of icy debris starting around Neptune's orbit at 30 AU and extending out to maybe 50 AU.
And Pluto lives out there?
Exactly. The Kuiper Belt is home to Pluto, which is the most famous resident, and for a long time was considered the ninth planet. It's now classified as a dwarf planet. It's the largest known object in the Kuiper Belt proper. It has a weird, tilted, oval-shaped orbit that actually crosses Neptune's path sometimes, but they're in this stable resonance, so they never collide.
And it has moons.
5 known moons. The biggest is Charon, which is huge compared to Pluto, about half its diameter. They're so close in size and orbit each other around a point outside Pluto that some people call them a binary dwarf planet system.
Are there other dwarf planets in the Kuiper Belt?
Yes, several. We know of Haumea, which is weirdly elongated, spins super fast, and even has rings and 2 moons. Makemake is another bright one. Quaoar. Orcus. These are substantial worlds, round under their own gravity, but they haven't cleared their orbital neighborhood, which is part of the definition of a planet now.
Okay, so Kuiper Belt, then what?
Then you get the scattered disk. This region overlaps with the Kuiper Belt, but stretches much, much further out, maybe hundreds of AU. The objects here tend to have much more eccentric, tilted orbits. The idea is that these are Kuiper Belt objects that got gravitationally scattered outwards by encounters with Neptune, especially during its early migration phase.
And this is where Eris is, the one that caused all the Pluto trouble.
That's the one. Eris is a dwarf planet in the scattered disk, and when it was discovered, astronomers realized it was actually slightly more massive than Pluto. That really forced the question, what is a planet? Eris has a really wild orbit, very tilted, very eccentric. It has 1 moon, Dysnomia. Gong Gong is another recently recognized dwarf planet out in this scattered region.
And even further out than that?
We start finding extreme trans-Neptunian objects, or ETNOs. These guys have orbits that take them incredibly far from the sun, hundreds or even thousands of AU away, way beyond the main influence of Neptune.
Like Sedna.
Sedna was the first big one found. It's this reddish object on an enormous 11,400-year orbit that never brings it anywhere near Neptune. Its closest approach to the sun is still way, way out there. This led to the idea that maybe it's part of an inner Oort cloud or perhaps influenced by something else.
Ah, the mysterious planet 9.
Exactly. The weirdly clustered orbits of Sedna and some other ETNOs are the main evidence that's led some astronomers to hypothesize there might be another large planet, maybe 5-10 times Earth's mass, lurking way out in the darkness, gravitationally shepherding these smaller bodies. It's still a hypothesis. Others argue it could be observational bias or just coincidence, but it's a really exciting possibility.
And beyond that speculation, there's the Oort cloud.
Right. This is the theoretical outermost region of the solar system, a truly vast spherical shell of maybe trillions of icy objects, comet nuclei, extending perhaps 50,000 AU out, maybe even further, almost halfway to the nearest star. We can't observe it directly, it's too far and faint, but we think it's the source of all the long-period comets that occasionally swing into the inner solar system. It's the very edge of the sun's gravitational kingdom.
Wow. So, okay, we've gone from the sun out to this theoretical edge. Let's pull back. Where does our entire solar system sit in the grand cosmic scheme?
Good question. If you zoom out, our whole solar system is just drifting through what's called the local interstellar cloud. And that cloud is inside a bigger region called the local bubble, this huge cavity in interstellar space, probably carved out by ancient supernova explosions millions of years ago. And all of that is located within one of the spiral arms of our Milky Way galaxy, the Orion Cygnus arm.
So we're in a spiral arm. And the nearest star?
That would be Proxima Centauri. It's a small, faint, red dwarf star, about 4.25 light years away. And what's really exciting is we know it has at least one planet, Proxima Centauri b, which is roughly Earth-size and orbits in the star's habitable zone where liquid water could exist.
A potentially habitable world right next door, cosmically speaking.
Relatively speaking, yeah. The Alpha Centauri system, which Proxima is luckily part of, is our closest stellar neighbor. Our own sun, meanwhile, is orbiting the center of the Milky Way galaxy, where that supermassive black hole Sagittarius A resides. We're about 26,000 light years out from the center, and it takes us around 240 million years to complete one lap, one galactic year.
And our location is kind of fortunate, isn't it?
It seems to be. We're not too close to the chaotic galactic center, and we're not right in the busiest parts of the spiral arms where there's more intense radiation and more frequent supernovae. This relatively quiet galactic neighborhood has probably been pretty important for allowing life to evolve and persist on Earth for billions of years.
It's just amazing to think about how our understanding has grown, from people thinking Earth was the center of everything.
To realizing we're on a small, rocky planet orbiting a typical star in a vast galaxy. Yeah, the journey of discovery is incredible. For centuries, the geocentric model, Earth at the center, held sway. Then you had pioneers like Copernicus suggesting a sun-centered, heliocentric model. Kepler figured out the orbits weren't perfect circles, but ellipses.
And Galileo with his telescope.
Right. Galileo didn't invent the telescope, but he was one of the first to really point it upwards. Seeing moons orbiting Jupiter was huge proof that not everything orbited Earth. Huygens figuring out Saturn's rings, discovering Titan, bit by bit, the picture changed.
And Newton tied it all together.
Pretty much. Isaac Newton's laws of motion and universal gravitation showed that the same force keeping apples falling to Earth was also holding the moon in orbit around Earth and the planets around the sun. It was revolutionary. Then, discovering Uranus, then Neptune predicted mathematically before it was seen, based on wobbles in Uranus's orbit.
And then the space age just blew it wide open.
Absolutely. Starting in the mid-20th century, we began sending probes, visiting all the known planets by 1989. We've landed on Mars, Venus, Titan, asteroids, comets. We've flown through Saturn's rings, sampled a comet's tail, even touched the sun's outer atmosphere with the Parker Solar Probe. We landed humans on the moon with Apollo, and we're planning to go back with Artemis.
And that whole reclassification to Pluto.
Yeah, the 2006 decision by the International Astronomical Union to define planet more formally, which led to Pluto being reclassified as a dwarf planet. It was controversial for some, but it really stemmed from discovering Eris and realizing there were likely many more Pluto-sized objects out there in the Kuiper Belt. It sparked a lot more interest in these distant icy worlds.
What an absolutely incredible journey we've taken right through our solar system, from its fiery birth, out past the giants, to those frozen frontiers, and even looking at our own story of figuring it all out. It really is just a dynamic, awe-inspiring place we live in.
It truly is. And it's a reminder that discovery is never really finished, Even with everything we've learned, there are still so many mysteries out there. The solar system is constantly changing, constantly surprising us.
Definitely. So thinking about all that, the hunt for Planet 9, the huge unseen Oort cloud, the sun's own future, as you look up at the night sky, what's the one big question about the solar system, its past, present, or maybe its future, that you find most fascinating to chew on?